Well, hello, and thank you for joining our latest sustainability webinar hosted in association with Honeywell Aerospace Technologies. Can hydrogen power aviation to a zero carbon future? Now, hydrogen is everywhere. In fact, as we all know from our school science lessons, it's the most abundant gas in the universe. But it's also arguably the most exciting potential fuel source that we have when it comes to the promised transition from a carbon-dependent aviation industry, with companies from Airbus to a number of well-funded startups pursuing the technology. But how do we produce hydrogen in the volumes we will need and store it in a state that we can use on board and on the ground? How do we design safe, reliable, and efficient propulsion systems that can be powered by hydrogen? And how do we design aircraft around those propulsion systems? I'm hoping that my distinguished guests today will have the answers to at least some of these questions. So let me introduce them. Firstly, Paul Hutton is the CEO of UK-based Cranfield Aerospace Solutions, a pioneer in developing scalable hydrogen electric propulsion systems. Now, Paul has worked for Thales and Airbus and is a former Lieutenant Colonel with the Royal Electrical and Mechanical Engineers. So, welcome, sir.
Hello, Madam.
Urian Kellerman is the CEO of Fokker NextGen, a company that traces its roots to the famous Fokker aircraft company and is today aiming to bring to market a regional airliner that can be powered by hydrogen, as well as SAF and kerosene. James McMicking is the Chief Strategy Officer for ZeroAvia, which is creating a family of hydrogen electric powertrains for regional aircraft. James has worked for the Aerospace Technology Institute and FlyZero, a research project looking at zero carbon technologies for aviation. And finally, from our sponsor, Honeywell, Senior Director of Engineering, Phil Robinson. Phil is in charge of technical strategy, partnerships, and advanced technology developments that support Honeywell's pursuit of reduced and zero-emission aircraft and systems. He previously ran a UAS fuel cell manufacturer acquired by Honeywell in 2020. So welcome, all of you. Before we move on to discussing the potential of hydrogen, a quick run through the format if you're not familiar with these FlightGlobal webinars. We're live for the next 56 minutes or so, and we welcome your questions to the panel. Please use the Q&A icon at the bottom of your Zoom screen, not the chat button. And I'll try to get to as many of these questions as possible over the course of the webinar. So, Paul, let me start with you. Very briefly, tell me about how Cranfield Aerospace Solutions hopes to crack the hydrogen electric conundrum. In other words, how do you make this technology scalable? Now, you've been working with a number of partners on this, I understand.
Yeah. So our aim is to take that very first step, getting the first zero emissions hydrogen fuel cell passenger carrying aircraft flying in the 2026-2027 timeframe. What we're doing is we're starting off with a small aircraft, a sub-regional aircraft, 9-seat British Northern Islander. It's a short hop aircraft, so it doesn't typically need a great range for its commercial viability. And we've chosen the aeroplane to make the first step as easy as possible, because having been in the business for over 30 years, we know this first step is going to be hard. And before you worry about scaling, you've got to prove that you can safely fly these aeroplanes in a way that can get certified and that you're happy to put passengers on. So our first step is to focus on an aeroplane that is that easier first step, and it will use gaseous hydrogen. And the importance of that, which I'm sure we'll come on to later, gaseous as opposed to liquid, is that the provision of liquid hydrogen logistically at airports, to move it to airports, to store it in airports, is in itself a challenge, even before the aircraft designer solves the problem of incorporating it into the aircraft itself. So we we're very comfortable that gaseous hydrogen is logistically available today. So we can get ahead and get real aeroplanes flying, which is the most important step, using solutions that operate with gaseous hydrogen, which means you're limited in range initially until the liquid hydrogen arrives. But the good thing about this, and what's important for everybody to understand, is for hydrogen fuel cells, the when the fuel enters the system, it's always gaseous. So everything that we do at this early stage around getting real aeroplanes flying on gaseous will benefit us when the liquid hydrogen fuel arrives later. And everything that we do in terms of getting to the right power density to get a real aeroplane flying can be then scaled up, because having solved the engineering challenges, it's then an incremental task to scale them up to larger power needs and longer ranges. So that's our aim.
Great, thank you for that, Paul. Jurian, we all remember Fokker. Very briefly, just tell us what your connection is with that brand, but then tell us as well about how feasible your plans are to develop an actual airliner that can be powered by hydrogen.
Well, thank you for having me. Fokker Next Gen stems from the old Fokker Aircraft company. After the demise, our parent company acquired the rights of the Fokker IP to develop new aircraft based on Fokker, with the Fokker name. So we have been using this experience and heritage to develop new aircraft. First evolutions of Fokker aircraft, but since 2019, we saw that any new entrant to the market has to contribute to less CO2 emissions in the aviation industry. So we set out to do just that. We try to go on the path of modifying existing Fokker 100s to fly on liquid hydrogen, but however, that doesn't work out economically for us. So we are now developing a clean sheet hydrogen combustion 120-seat airliner with a range of 2,500 kilometers or 1,600 miles. So with that, we would be able to address about 30% of the CO2 emissions of the aviation industry. We are doing this not alone. We see it as a collaborative effort. So we are working with well-established supply chain partners to make this work. For instance, for the engines and other major parts. And we are very happy with parties like Cranfield and also ZeroAvia, paving the way also for infrastructure on airports, so that a few years later, the airports can also host liquid hydrogen-powered aircraft.
Thank you, Jurian. Thank you. James, ZeroAvia is one of the first movers in this sector. And as well as advancing the technology, you've been busy raising money, including from some big names like IAG, American Airlines, and the Scottish National Investment Bank. So maybe tell us a little bit about your finance raising, but also about progress with the ZA600, your first product, and where you are in terms of the program, in terms of industrialization, because you have already been flying with the technology.
That's right. Yeah, thank you, Murdo, for that introduction. Great to be here. Yeah, we're really pleased with the financing progress we've made, recently closing our $150 million Series C round, including investment, as you say there, from Scotland, as well as the UK Infrastructure Bank. And these things are going to help us take our engine now through to certification, and also start progress on industrializing that technology. And we need to build up the supply chain and the manufacturing system to deliver that as part of the certification program. So we're making great progress on that front, already well into qualification of components, so going through all the environmental testing that you need to put these things through to get them proven safe. As you say, we've flown 3 aircraft already, and we continue to operate our Dornier 228, which has one of its engines replaced with the hydrogen electric plant, and using that platform as a way of testing other technologies and future advancements. We've got a lot of in-house technology right across the powertrain, from motors, inverters, fuel cell systems as well. and we're investing in the future scale-up of these systems. So we're looking ahead to the ZA2000, which will power the regional turboprop, a 2 to 4 megawatt power plant. And this will require new technology beyond what we are putting into our ZA600 engine. But Paul said something very important. That first step is critical, and we're very focused on that. As again, small aircraft, sub-regional, gaseous hydrogen. That's the first thing we're going to certify, and we'll be operating, within the sort of 26 timeframe. And because we've got a lot of in-house technology, we're also providing to customers our hardware, component hardware, so motors and inverters, and fuel cell packs. So we're finding that that's a good market opportunity for the business as well. So making good progress on certification and industrialization.
Right, and just to clarify, of course, James, your customers are essentially the companies that are developing aircraft. You're going to be supplying the powertrain to those.
That's right.
Those
We're retrofitting planes as the rapid route to market, and we're working with the OEM partner to do that. So first product, Cessna Caravan, doing that with Textron, but also the clean sheet aircraft manufacturers that want future power plants, direct to them as well, as you say.
Okay, great. Now, Phil, Honeywell, of course, you're not in the business of developing aircraft, but you are working with a host of advanced air mobility and disruptive propulsion startups. How do you view the potential of hydrogen as a game changer?
Thanks, Murdo. I really see hydrogen as a really important tool in our toolbox to achieve zero-emission aviation. Hydrogen is not going to be everything everywhere all at once. There's lots of transition. SAF will play a really important role. Hydrofuels or synthetic SAF will play a role. We see hydrogen, as you've heard already today, starting with very often smaller aircraft, moving to larger ones. It's easier to solve some of the logistics and scale problems, solve them there, and then move larger. We see hydrogen fuel cells as being important, but also hydrogen combustion. So both of those have a role to play. And there's absolutely regional differences. There's certainly a greater short-term emphasis on hydrogen development in Europe than in North America. In North America, we see more emphasis on the SAF development. And but long term, I think to achieve that future that as an industry we want to get to, it will require SAF and batteries and hydrogen is definitely an important piece of that.
Okay, thanks, Phil. Well, hydrogen is what we're going to be focusing on today. I know in other webinars we've talked about electrics and various other, and SAF. But just on hydrogen, and I'm going to take a question from the audience here that has just come in, and it's one that I was going to be asking anyway, and it's really about that role. Phil, you alluded to it, that difference between Europe and the US. What sort of incentives does the industry need from government? And also, what help does the industry need from the sort of established OEMs and the likes of the established players in this industry, like Honeywell? We've already seen a high-profile casualty in this market, universal hydrogen. How fragile is this sector? And what incentives are needed to really sort of give this sector the sort of kickstart it needs? Paul, do you want to come in on that one?
Yes. So there's various things that government can do to accelerate the adoption of these technologies. So, and some of them are counterintuitive. So we'd like to see, for example, in the UK, the government introduce policies which push airlines, domestic airlines, on sub-regional and regional routes to adopt zero emissions aircraft. So, for example, if there was a policy that said that any flight of 60 minutes or less by 2028 had to be using zero emissions aircraft, that forces the airlines that operate those type of flights to look to engage with organisations, businesses like ourselves, to find product. And then when you're looking to raise money, you've got buying signals from the market saying that they want to buy your product. So the private equity and venture capital organisations are more likely to put their money into you. So I think those sort of, perhaps governments see these things as risky policies to introduce, because what happens if you can't deliver the right type of aeroplane in the right time frame? But I think if we want to go green, if we want to reduce emissions, government needs to take these bold decisions. So that sort of indication can help and push the market in the right direction. I think in terms of direct funding, it's good to see, for example, in the UK, a big focus in recent months on the National Wealth Fund, the idea of the government introducing funding to put into key industries, one of which is zero emissions technologies. What that does for us, and I'm sure Zero Avia is in the same place, we'll raise most of our money in the private markets. But what the private markets, equity markets, like to see is the host government putting some money in themselves. And that then leverages in a multiple of funding from private equity and venture capital organisations. So I think both on the policy side and on the direct funding side, governments can do more if they want these technologies to be deployed, in our case in the UK, and indeed manufactured, in our case.
Okay. Jurian, do you want to come in on that? In
I,
terms
I
of support
fully
from the
agree,
EU?
of course.
Yeah.
It does help when the government supports these programs with the regulations, but also take, for instance, a stake in those companies developing these solutions. You see also in the EU that there's big programs like Clean Aviation in which we participate. That really helps, also providing credibility in the market and also to potential customers. So that really helps. In the end, of course, we are all looking for a sustainable business model in that sense. So the government cannot keep supporting these solutions. So in the end, it needs to these aircraft needs to be cheaper to run than a conventional aircraft. Otherwise, it will not stick. So in the beginning, we will need help from government, maybe with some carbon tax or incentives for zero emission aircraft. But in the end, and that is also why we developing solutions for this market, we see that liquid hydrogen or hydrogen will be cheaper than kerosene in future.
Okay, thank you. James, we talked about support that you've had from UK Investment Bank, from the Scottish National Investment Bank. What other incentives, perhaps maybe fiscal incentives as well, do governments need to look at to give the industry the sort of kickstart it needs?
Yeah, I think all the support that's going into the innovation, the R&D is very good, and that's helping us get the technology up to a level of maturity where we're confident it can work. But clearly, bringing a new zero emission product to market and all of the infrastructure that's required to support it operationally and to maintain it is a very different ask than buying a slightly more efficient aircraft that operates within the existing system, right? If you're the airline, and we're not at scale yet. And I'm confident when we do get to scale, it will be economically competitive and sustainable, but we need help to bridge that gap. It's not, I don't think, reasonable to expect it to compete day one with those existing solutions on a commercial basis. So I think that's an important role. I think the airlines, the operators that take these technologies on should be rewarded for bringing something that is clean and efficient to market first. I think capitalizing the scale up we need other instruments and support to finance that activity, so we can get to economically efficient scale in the supply chain and in the delivery of the aviation system that goes with it. So you're going to need a combination of measures to bring it about, and then a glide path down to a point where it's over to the industry alone. And I think thinking about that transition and how government can play an important role in kickstarting and catalyzing it's essential. Otherwise, I think we can get stuck at the TRL 6 points in the industry and struggle to make that transition into real commercial industry.
Thanks, James. Phil, do you want to come in on that point?
Sure, and I certainly agree what the other panelists have said. Two critical elements of different parts of the government we don't often think about. One is the infrastructure. Most airports are owned by municipalities and much smaller entities than a federal government. And so getting the support for infrastructure at that low level will be absolutely critical. Of course, most municipalities don't have much money. And so being able to help them from a larger standpoint will be critical to getting this rolling out. The other piece that is really tied in with the government is the regulatory aspects of getting aircraft certification. How safe is hydrogen? How do we make it safe? How do we establish standards so that we can all be confident it's safe? And there are certainly groups like SAE EuroK that are working on hydrogen standards for aircraft right now, but it will take the involvement of EASA, of the FAA, to point to those standards and say, industry, adhere here, and we will, bless it and let you fly, and that will be critical to enabling the market.
Thanks,
Can
Phil, and I hope
Can
to
I
come
say
back.
something?
Yes,
Can I say something
Jurien,
about that?
please.
Thank you, Phil. For those last points, I'm an entrepreneur at most, of course, seeing opportunities. So regarding your first point of airports, we are also educating airports and regional airports that it could provide new business models for them as well, because the market of hydrogen production is not divided yet. So they could be their own hydrogen supplier for the airport and make some money there. That's something they do not really see yet. So there's room for improvement there. And to take your other point, we are in discussion with the EASA for the regulations, which is very important, of course. But I also noticed there's a discrepancy between FAA regulations or potential regulations and EASA. So we also together might lobby for more discussion between those regulatory bodies to make a global standard.
Excellent. You both there brought up the subject of infrastructure and also certification, and that's two topics that I do want to just pursue a little bit further. I mean, there is an argument that, no matter how good the technology that you produce is, without the infrastructure, without the widespread availability of hydrogen fuel, this transition doesn't really work. And that brings me to a question from the audience here, anonymous attendee. Hydrogen is not stable in nature, so it has to be manufactured, but it's a super mature market in that it's been used to make fertilizer for decades. So how are you planning to scale the fuel infrastructure at a pace compatible with engine development and the Paris Agreement? That's the question from the attendee. So I don't know who wants to come in on that. Generally on infrastructure, Paul, you referred to this earlier. What's your view on how that infrastructure gets created, gets scaled up?
So I think the danger with looking at this sort of problem is that people very quickly start at the very large airports, servicing very large aircraft with huge fuel needs. And actually, that's not the place to start. We do have to get there, but many of the problems of providing the fuel, the rules, the regulations, the policies, and the technologies can be solved at the lower level, at the small aircraft needs. So if you take, for example, a Britten-Northern Islander flying in Scotland, a full fuel load is 34 kilograms of hydrogen. You could, in its simplest form, you could bring that in bottles on the back of a truck and store it in a tank on the airfield, or indeed an ISO container-sized electrolyzer using green electricity produced off the coast of Scotland. So, but by starting there, the useful step that create, again, like the technology on the aircraft is, in order to deliver that fuel into the airport, we've got to agree the rules, the CAA rules for how the airport receives that, how the airport stores that, how the airport is able to deliver it to the aeroplane, what the rules are for testing that fuel in case there's that. All of those things can get solved. So, we tend to worry about the scale-up challenge. Think all of those things are going to have to be sorted at the same time. But all those rules, regulations, processes, and procedures can be done when actually the demand for the volume of fuel is relatively small. And then as you're needing to increase the amount of fuel being provided, that's only happening over a prolonged period of time as the technologies for the larger aeroplanes with longer ranges are coming on board. So I think it then becomes less of a stepped problem. It's an evolutionary problem. The view that we take is very much get in early, solve the problem on small aircraft. And I think, again, often in the market, we look at these smaller aircraft and think, well, these aren't going to have a dramatic impact on the CO2 production, CO2 impact of aviation across the world. Well, they will, in that if you solve the problem with the small aircraft, you've taken that first step. You've solved many of the problems, both technically on the aeroplane, but also logistically on the provision of the fuel and from a policy and rules procedure in the airports. And then we can scale that up so that we will get to the large aeroplanes having the big impact on the environment. I think it's that incremental approach. Don't worry too much about where we need to end up. Start with where we are today.
That's a really good point. So the scaling up is not just about the size of the aircraft. It's also about where the hydrogen is available on the ground, and perhaps small remote airports are where it all starts, rather than at the Heathrows and the JFKs of this world. That's very interesting. Urian, do you want to come in on that, on the infrastructure challenges? Because
Yes,
you're
of
obviously
course.
going to be developing a regional aircraft that your customers will need that infrastructure. They might love your aircraft, but if they can't get the hydrogen to fly it, it's not going to be much use.
I totally agree with Paul on this. So we are working with several regional airports in Europe, also in the Interreg program in Europe around the Baltic Sea. So there's 25 regional airports that we are working with. Also in terms of regulations, what it takes to have hydrogen on the airfield. Also airside, so we need to work with air traffic control in Europe as well, because they control that area. So it's complex and complicated, but again, there we are making progress in that sense. To add to what Paul said, even a large aircraft like ours to fly 2,500 kilometers or 1,600 nautical miles, we only need 2,000 kilos of hydrogen. So if you look at the numbers, it's not that big of an issue. You can move it with a truck to a remote airport if there's no local storage there. So, and these regional airports, they deliver, they have, I don't know, 3, 4, 5 flights a day. So it's perfect. It's not a real issue. And that's also what we are discussing with these airports. And then we see it scaling up, maybe from a hub and spoke. And also, although would like it, I don't see airlines exchanging their 100 conventional aircraft for our hydrogen-powered aircraft anytime soon. So they will start with 5 on some routes. So it's easy to scale. Let's first work with it, see how these aircraft work, also see the benefits of hydrogen, because we tend to see the problems, but there's also a lot of benefits in using hydrogen in aviation. We learn from that. We will have customer acceptance, buying the tickets, and then we scale up.
Okay. James, I'm going to ask you where you see both on the infrastructure and how that relates to where the markets for these aircraft are going to be initially. Is it going to start in the GA world, in the regional transport world? Where is it going to start, and how will that scale up? And how do you see that rollout of the infrastructure?
Yeah, we've as a business, we've done a lot in this space, and obviously we're today fueling an aircraft occasionally for flight testing activities. We've built our own on-site production, mobile refueler, and pipeline for an airport. So we have experimented and tested the protocols for doing aircraft refueling. I agree with what the others have said here. If we look at the long term, it can be overwhelming, and this is not a good place to start. We take small steps to get there. We do have a vision, a very clear vision of what the future aviation system can look like, and distributed on-site production of hydrogen is definitely part of that vision in our minds, and that will change the role of the airport as we go to net zero economy. But early steps will be about flexible, deployable infrastructure that can be moved, deployed as the network expands and grows. So we've developed what we call mobile storage and dispensing vehicles. These can carry large quantities of fuel for the size of aircraft we're initially operating. As Paul said, for them, around 35 kilos, for us, around 50, 60 kilos for the first applications. And these vehicles can drive onto the airfield, refill the aircraft, no major kind of laying of concrete and infrastructure required, and either be filled up at a dedicated production site or an offtake as part of that other industrial use case for hydrogen. As we say, we're already producing hydrogen, so we can go and take fuel from those locations as well today. And then as demand grows, the logical point will be reached when it makes sense to make different investment decisions on how you provide hydrogen to the aircraft, and that will then continue to drive down the cost of that. So that's kind of how we see the network taking that first step and then scaling up. And in terms of first applications, we're beginning in the regional segment. And one of the nice things with commercial aviation as a use case for hydrogen is you have a finite number of nodes at which you need to fill up the aircraft, right? And it's a controlled professional environment in which you're doing it as well with hydrogen. So this is a great environment actually to be deploying something like this. You can standardize, professionalize the entire process. Also, we find that a lot of the networks we're going to be servicing allow the tankering of fuel, and of course you don't pay a huge penalty on the fuel itself with hydrogen. It's a very light part of the overall system. So that means you don't have to provide fuel at absolutely every location to begin with. And on average, around half of the airports in the network need fuel to get operating. Okay, and then from there you can expand. So there's some sort of very practical things we can do at the early stages of rolling out hydrogen for aviation.
Okay, great, thank you. Phil, do you want to come in on that?
Really, the only thing that I'd add is that if we take a step back, and this the person that posted the question kind of hinted at this, hydrogen is only a zero emission fuel if it is generated in a zero emission manner. If we're simply moving the carbon from the combustion in the aircraft back to where the hydrogen is made, we're not really solving the problem. And so the other area that governmental support is really important in is providing for green hydrogen. And of course, we're starting with gray hydrogen. That's our history, hydrogen that comes from petroleum. Now there's a lot of emphasis on blue hydrogen, where we're converting from propane or methane, but also with carbon capture, so that we're capturing that carbon, and so we are truly net zero with that. And then pink hydrogen from nuclear. There's lots of different sources of hydrogen, but as we transition over a time, again, in starting with scale that is small and going to larger and larger scale in the hydrogen supply chain, that will also be required for us to achieve this vision.
Yeah, maybe I could just add one more thing on the hydrogen discussion. So SAF fuels require hydrogen in the production process, whether it's a biofuel or a power-to-liquid fuel. And given the the amount of SAF that is required by the existing aviation system, the reality is most of the hydrogen production will be needed in that part of the aviation sector rather than the direct use in the near future, right? Until we can make this transition. So yeah, absolutely, the whole industry needs, as Phil says, big scale up of clean hydrogen, whether it's for direct use or SAF use.
It's very interesting you said that, James, because my next question was going to be from the audience, and you just preempted a question that, forgive me if I've got the pronunciation wrong, Ahmed Rekibudin has asked, which is exactly about that, that hydrogen is needed for SAF, for power to liquids or PTL fuels. If hydrogen is available, would it not make more sense? Would it not be more efficient to use that hydrogen to make SAF on existing engines or adapted engines rather than inventing a whole, reinventing the wheel with hydrogen propulsion? Does anyone, maybe Paul, do you want to come in on that point?
Yes, so I think because of the advantages that you mentioned there, SAF does have a part to play. And I think somebody said at the start, we're going to need a portfolio of technologies to reduce the CO2 emissions of aviation. And SAF has some advantages, and particularly its use in existing engines, but it has disadvantages as well. So, as of today, the maximum amount of SAF you can use in an existing engine is about 50%. If you want to use SAF completely, you're going to have to redesign those engines to operate with SAF safely without huge amounts of maintenance every flight. So it still produces CO2. So when you burn SAF, you produce the same amount of CO2 as conventional fuel. So it's only a net solution, not a true zero solution. And building on the point that James just made there, it takes hydrogen. It uses hydrogen in its manufacture. So in terms of the cost of that SAF, it's inevitably always going to be more expensive because it's the cost of making the green hydrogen. You've then got to go through the process of turning it into SAF, and you've added more cost on there. So I think SAF will play a part, but ultimately there's no way that we solve aviation's problem without a true zero emission solution, and the only credible one at the moment is hydrogen.
If I may add to that,
Please.
what we've done with our aircraft, it will also be able to fly on sustainable aviation fuels. So that will help market introduction because of that will help. I fully agree that we need SAF to help the growth in aviation industry. That somewhere we need 40,000 new aircraft in the next 20 years. If you look at the big incumbents in the market, they produce about 70 aircraft each conventional per month for the next 10 years before our products come online. So and they will fly again for another 20 to 30 years. So we need SAF to make them a little bit cleaner, but it won't solve the problem. So ICCT also produced a report recently that from 2035 onwards, we need zero emission aircraft on the market to reach our objectives of net zero in 2050. And we also need pragmatic solutions to make this work. So we can only use state-of-the-art technology now to be able to have certifiable aircraft in 10 years' time, and have then we'll have 15 years to ramp up to some kind of production that will make a dent in the CO2 reduction emissions. So we need the solutions now, actually, and not later.
May I add as well?
Of course, yeah.
Okay, great. Yeah, I mean, I completely agree that SAF has this really important role to play in the transition, because the fleet is going to take a long time to replace with these new solutions, and for us to scale these solutions up to address all of the market's needs. So we need SAF. The problem is finding enough of it, and you have different inputs that can go into production of SAF. So obviously bio waste sources combined with the hydrogen to build the molecules. but there's a limited feedstock of that, and it won't be enough for the entire industry by a long shot. And then you're into other ways of producing SAF, such as what we call power to liquid. So you capture the CO2 either directly from the air or from industrial processes, which you might question whether those industrial processes can be decarbonized in the first place. And then you go through chemical process to build the molecule. And those things require more capex on the production side. Okay, you save in terms of the delivery to the aircraft and the aircraft itself, because it can fit into the existing system. But some of the upfront production of the fuel will require vast amounts of capex and even more energy, because all these things need to be run by energy. And by some estimates, if we're in a world of power to liquid, you'll need around the same again in terms of energy infrastructure to drive everything and to build those molecules. So that comes at a huge cost to the environment and economically speaking. So I think hydrogen and SAF will work together, and hydrogen needs to scale fast, so we avoid a future of very expensive decisions on only running on SAF.
Thanks for that. I just wanted to talk, and Phil brought this up earlier, the whole certification issue. This is perhaps one to start with Paul and James, because you are the ones developing the power plants. But what are the, maybe without getting too technical, without giving away too many state secrets, what are some of the challenges of making this technology work with the with fuel cells, with the getting the hydrogen on board the aircraft, storing it on board the aircraft at the right temperature? Maybe just run us through how you've overcome some of these challenges, and then how you're going to be convincing the regulator that it's safe. Paul, do you want to start on that? Yeah, sorry.
Okay. Yeah. So
Paul, then James.
yeah. In terms of how we've approached it, so some of the big challenges with fuel cell systems include thermal management. So a conventional engine loses most of its heat out the exhaust. A hydrogen fuel cell system doesn't have an exhaust, so you've got the problem of getting all of that heat out of the system. Now that in itself is a challenge, but you've then got to get rid of that heat without introducing drag. So working out how to remove the heat and to do so without basically creating an air brake for the aeroplane is a big challenge. You then got to deal with the fact that you're trying to replace the power on the wing or on the nose of the aircraft that's currently being provided by a conventional engine that has got many decades of development behind it. And we're dealing with, in an aerospace context, electric motors and hydrogen fuel cells that are very immature. So trying to get to the power density needed to replace that conventional engine is tough. And then trying to get to that power density, but package it in a space that's available, because you're converting airplanes that weren't designed for these technologies, is really tough. So it's bringing all those things together. The level of power density needed to fly the airplane, packaged in a space that is actually available in the aircraft, and therefore in a way that in itself doesn't increase drag overly, and getting rid of the heat that you're producing during that process. So, but these are just engineering challenges. This is what aircraft engineers are good at doing. So that's just it, breaking it down, working out what the problem is, solving the problem, and that's what we do. And then when you go to the certification, the Civil Aviation Authority, the FAA, they don't get worried about, oh, this is a new technology, how are we going to deal with this conceptually? They just break it down. So what is the safety risk of that particular activity that you're going to do on the aeroplane? What evidence can you show me to show me that that particular piece of technology is at least as safe as the technology it's replacing? It's a very structured process that the regulators have. And certainly we've been doing this sort of certification work for over 30 years. And up until we were developing our own products, we tended to do it for some of the most demanding aerospace customers in the world, the Airbuses, the Rolls-Royces, etc. And we're used to coming up across a problem, solving the problem, and solving it in a way where we can deliver the evidence that the regulator will be comfortable with that solution is safe to fly. So it's just following those standard engineering, aerospace engineering practices. there are no problems with these technologies that are insurmountable.
Thanks. And James, what were the biggest onboard challenges, technical challenges that you've had to overcome?
Well, I think, yeah, first of all, Paul's spot on with all of those challenges. We're in the same game, so you're going through the same things. So getting power density up and all the packaging size down is all part of it. There are a few things that we're advantaged by versus other engines. So, for example, the efficiency of the overall power plant is higher than the turbine. So, in terms of how that helps us is obviously carrying less fuel on board than you'd otherwise have to carry for a given range, a given mission. With a combustion engine. So that's something in our favour, but we're all working hard to compress the size of these things down. You have another design advantage in the sense that you don't need all of the system mechanically connected. Right, with a turbine, you have to have a direct line, mechanical line between, obviously we're extracting the energy from the gas through to the propulsor. With a fuel cell system, you don't need to do that. You can have your power produced in one place and then routed by flexible lines, cables to the motor. So this introduced some kind of interesting opportunities, particularly for the aircraft designer, to think about how they can take some advantage of that and make a more efficient aircraft. So these are all kind of interesting areas that we're playing with. If you look back at the history of aviation engines, there's generally something disadvantaged by the introduction of the next sort of paradigm of technology. So you go from internal combustion to jet. The early jet engines were horribly inefficient compared to the reciprocating engine, and it took about 30 years to reach the same level of efficiency. Now, for us, we're going to be more efficient at the outset, but it's going to probably take us some years to get close in terms of power density. And we're taking some of those early steps. So, within the business, as I mentioned earlier, we're vertically integrated on the technology. To overcome the thermal management challenges, we're developing high temperature fuel cells. So what that means is we've got a much greater difference in temperature between where the fuel cell wants to operate and the air you're using to cool it. And that allows us to strip away a lot of the what we call balance of plant that's used to maintain that fuel cell condition operating point. So we lose weight, we lose some packaging space, we reduce drag as a consequence. That's an example of how these type of engines are going to scale to larger applications.
Thanks. Urian, you've got the challenge of not just convincing the regulators that the propulsion system is safe and works, but you're having to get a whole aircraft past the regulators. How are you approaching that?
True. Yeah. Well, in some case, it's also more less complicated that we are doing, because we are working with established companies providing the next generation of gas turbine engines that are very efficient nowadays and will be 30% more efficient by 2035. They will be modified to run on hydrogen. So we're not going to change propellers or fuel systems, novel fuel systems. That makes it a little bit less complicated in that sense. Still, we need to make sure that the fuel storage and fuel system adheres to the rules and regulations. So that's what we're working on. If you look at certifying a complete aircraft, and we're looking at it from an aircraft perspective, you need a certified powertrain, you need a certified airframe, but also a certified combination of both. So I think it goes for ZeroAvia and Groundfleet as well. You need very close cooperation between the airframer and the powertrain developer to make this work early on, much earlier than aircraft that are now flying. So that is we need a lot of cooperation with our partners in this sense, but also with the regulator, because we've gone through the book also within clean aviation of certification, and I agree with Paul, of course, that it's a very structured route, but some of the regulations do not fit on hydrogen-powered aircraft. To give just one example, it says that the pilot needs to be aware of the amount of fuel on any aircraft at any time. It's very difficult to measure the amount of hydrogen in the tank because it's not just a liquid, it's not just a gas, it's something in between. So we need to work with them to make sure that we adhere to the regulations, and I agree with Paul that we demonstrate that is at least as safe as the current regulations. So those are the things we are discussing with EASA and hopefully soon also with FAA. As again, hopefully we can have worldwide the same regulations. Otherwise, it will be very difficult to make this work. So, yeah.
Okay. Thank you, Urian. Phil, I'm not asking you to come in on that, but I've also got a very specific question from you, from a member of the audience.
Okay.
So maybe talk a little bit on that certification side, but also I've got a question saying, and you talked earlier about the differences regionally, about how maybe Europe and the US are different with their approach to this. How can Honeywell, what can Honeywell do to help create this market in the US? And what services or support are you planning to provide? So let's maybe talk about the certification first, and then Honeywell specifically.
So yeah, on the certification front, we as Honeywell, as well as I think most of the folks on the call, are involved in the various standards committees and standards efforts, as are EASA and FAA. They've got people on these standards groups to make sure that we are breaking things down in a logical way, that we can be confident that what we're putting together is in fact safe. And of course, we're going to have lots and lots of testing to prove that to ourselves and to the regulators. So we have gotten to a point now in commercial aviation where the number of acceptable accidents is zero. We really expect absolutely safe transport, and so that's the bar, and it's a very challenging bar to get to with new technology, but the industry is oriented that way, and we're all pursuing that together. So and I think when you look at global companies like Honeywell, we've got a big development group in the Czech Republic that has an active clean aviation program working on a megawatt class fuel cell system. We are very involved with EASA and the regulatory bodies in Europe. We're also very involved with the ones in the US, the ASTM, as well as SAE here, the FAA, and here in the US, we're working on hydrogen combustion technologies, sensor technologies. There's all of these pieces that go into making this a whole, and there's a role for us big global companies, but there's also a big role for little startups that have a great idea for a new way of sensing how much hydrogen's in a tank when it's half liquid and half gas, or how to make a fill nozzle that works 100% of the time when it's used by a relatively non-technical person. So there are huge opportunities for little companies as well as big ones.
Thanks, Phil. Well, we're about 5 or 6 minutes from the end of the webinar, from our scheduled time. So I'm going to ask you a final question, and I'd ask you all to answer in about a minute, if you can, just to get us cleanly to the end of the webinar on the hour. And I often ask at the end of these webinars, if we come back in a year's time, where will the sector be? But I think we're going to extend the time scale in this case to maybe the end of the decade. So if I were to ask you all, if you look to 2030, are we going to be realistically flying in hydrogen-powered aircraft? And if so, what will these aircraft look like? Are they going to be, 6-seaters? Are they going to be maybe 100-seaters? Are they going to be even bigger? So crystal ball time. I'm going to start with Paul. Where are we going to be? Where's the hydrogen propulsion sector going to be 2030?
Okay, so I think what we'll have achieved by then is you'll see lots of aircraft flying using gaseous hydrogen, smaller aeroplanes, sub-regional, possibly up to 19 seats. And I think where you'll see the scaling definitely is, in a way, sideways scaling. And what I mean by that is applying the same gaseous propulsion solutions to our other platforms. So you'll see its use in cargo drones, and I'm not talking about a little drone bringing you a package from Amazon. I'm talking about an airplane carrying 300 or 400 kilograms of cargo, but very low cost because it's a drone, and giving it 1,000 kilometers of range. I think in the big airplanes, you will see the gaseous hydrogen begin to be used in auxiliary power units, the diesel generator that sits in the tail and produces a lot of CO2 on the ground. I think as well, by the end of the decade, you'll start to see the first aircraft flying using liquid hydrogen. It won't necessarily be the single aisles and the twin aisles. It'll be down at the regional size of aircraft, but you'll see those in smaller numbers flying around the skies carrying passengers. So I think that's broadly where we'll be at that point.
Thanks, Paul. Urian, what is your prediction for the end of the decade?
Well, we will see a lot of green production facilities come online at the end of this decade, particularly in Europe, but also in the US. So that will give confidence in the market that hydrogen will play a role. I also see larger companies like Airbus, but also, of course, Avia, and hopefully us. Well, I'm sure us as well, demonstrating firm orders for aircraft. So that will also demonstrate that these aircraft will come. Together with the rules and regulations that have been a step further, I believe, in the next 5 to 6 years. I see a bright future for this. And hopefully it will also be helped that at the end of this decade, that environmental costs will be calculated in financial numbers of all companies, actually. So we can really see the difference in that respect as well. Maybe more in Europe than in the US, but it's coming.
Thanks, Urian. James, I'll ask you to be quite quick with this.
Super quick.
But, your predictions for 2030.
Yeah, super quick, because I agree with everything that's been said, pretty much. We may see also an expansion in the sub-regional use case on the basis that these things are zero emission, at scale, lower cost, and may become an attractive way in which to open up, new ways of getting around for different regions. And I think we may see commitment to a large aircraft program running on hydrogen at that stage. Okay, not in service, but the engineering effort spinning up by the end of the decade, based on the progress made, of course, in propulsion and storage of hydrogen.
Well, that would be interesting to see. Phil, do you want to just round off with your comments?
I think at the end of this decade, we will be able to fly on hydrogen aircraft if we want to. And I suspect everyone on this call will have flown on one because we will want to, but it will still be a novelty. I think the end of the next decade, we'll do it and not even notice.
Okay. Well, that's something to definitely look forward to, and that brings me to the end of what's been a fascinating discussion. I'm sorry I wasn't able to get round to more of your questions. We had, I think, more than 35 questions in total, which is a bit of a record for these webinars. So I think that shows what how engaged people are in this discussion and this subject. I'd like to thank all of our panelists today, as well as our sponsor, Honeywell, and to all of you for joining us today. Please keep an eye on FlightGlobal.com for details of our upcoming webinars, which include the final webinar in our Honeywell-sponsored sustainability series for 2024. So thank you all for joining us today, audience and panelists, and goodbye.